It does. So we don't have to bring A in, right? There's no A adsorption. That's why it's not in the numerator of this reaction.
You think B collides with an A particle is already bound to the counter?
Oh, are you saying, okay, so you're saying this reaction.
Yeah, but it's not like actually.
No, I understand. So what we've been talking about are this is called Langmuir-Hinshelwood kinetics, right? And that involves the reactions of two coadsorbed species. There is a different type of kinetics called Eli radial. I don't know how to say that. It's also in chapter 10. I think one of the parts of a homework problem asks you to look into that. But yeah, it's exactly what you described. I don't believe that exists in reality. I've never seen an example of a species come in from the gas phase and react with a surface-bound species. You have to understand that molecules that are in the gas are sort of by definition somewhat stable, right? So normally you have to break them apart a little bit in order to get them to react with other species. So this is just, it's not a very common, again, I've never seen it in a way that I actually believe that it's true. But it is a, it's got a Wikipedia page. I mean, it is a real thing. Eli radial kinetics are real. You can derive the same type of thing that we did here. You treat the adsorbed species Langmuirian, and then you just treat the gas phase species as gas phase, and you can still derive a rate equation. Yeah?
Why don't you believe that when a gas phase molecule have higher energy?
It's not about the energy, it's that it's fairly chemically inert. And so what catalysts do well is activate those inert species and stabilize otherwise unstable intermediates like radicals and charged species. And those radicals are now, for example, methane. And I want to react it with oxygen. Neither one of these things give me a lot of tools to react them together. Now, if I take methane and oxygen, unless I light a match, they're just going to coexist perfectly happily. Now, what does lighting a match do? It initiates radical reactions, and that's why you get explosions. But by themselves, these two things aren't really going to do anything. Now, if I expose them to a catalyst, though, what can happen is I can form this. I can form this. So, in other words, CH3 adsorbed, CH2 adsorbed, CH adsorbed. And I can also form adsorbed oxygen. Now, these species can react with one another. They're missing things, right? They're not whole. Methane is whole. It's happy. It doesn't want to react with stuff.
When you have a reaction like that, do you, if you reacted it in gas, it would like blow up and release a lot of energy? When it reacts in a catalyst, does the catalyst heat up a lot?
If you're doing oxidative reactions with methane, you run outside of the flammable limits because you don't want your reactor to blow. So you're either going to run in extremely, extremely rich environments, meaning a ton of methane, very little oxygen, or the opposite way. So for example, Helena Weaver's group does these types of reactions, and that's exactly what they do. I think they run in a, I believe it's very oxygen heavy, but I could be backwards on that. Yes?
I think what you were asking was, because there's that change in enthalpy of the exothermic, wouldn't the catalyst have to heat up a lot?
So any reaction gives off heat or consumes heat. It matters with catalysts too. And in fact, one of the ways that you try to mitigate it with catalysts is you mix in your active material with inert material. And that inert material can act as a heat sink or as a, sort of a heat well if you have an endothermic reaction. So there are ways of mixing your solid catalyst with inert material in order to improve the heat transport capabilities. But you don't have to worry about, you wouldn't run this where gas phase reactions could be occurring simultaneously, like methane combusting with oxygen in the gas. You wouldn't ever run a catalyst that way.
Is the enthalpy of the reaction in the gas phase related to the enthalpy of the
Yeah. They are the same, right? So we had all those elementary steps up here, and then we added them up, and they became this.
So the amount of heat released from a reaction on a catalyst should be the same as the amount of heat released from the gas phase one?
Yeah, it's independent of catalyst. If it's a real catalyst, meaning that it's not being consumed or produced during the reaction, it's inert. So you still have to start and end up at the same exact thermodynamic places, which are the gas phase species. Remember that thermodynamics, it's a state function, right? It doesn't matter the path you take. Kinetics does. But that's the barrier, that's not the reaction energy. The reaction energy is independent of path. Okay, but yeah, reactions with gas phase species are real. They're called, well, I don't believe they're real, but they are taught. Like I said, it is in chapter 10. I think one part of one of the problems asks you to derive the rate equation, assuming that that is the mechanism. And it's not hard to do.
Wouldn't you have the Eli Rydell, whatever it is, setup happening if you were running the catalyst under the same conditions where you do the gas phase reactor without catalyst?
Sure. I mean, in extreme conditions, yeah, you can make a radical that will react with something on the surface.
Well,
But
if the gas phase reactor doesn't get through a radical, couldn't you then?
I mean, typically gas phase reactions proceed through radicals. So I just kind of mentioned radicals. You activate a species and it activates another, and then so on and so forth. It's not always true, but it's often true. And certainly, if I make a hydrogen radical, if I somehow made this, and I had on the surface CH, it would pretty easily make CH2. But the number of real catalytic systems where that happens is astonishingly small and not that important. And it wouldn't really change anything if you treated it as a two-step reaction, where the first thing that happens is you adsorb, and then the second thing that happens is you react. It would change things just slightly. Okay, so the other thing that I want to mention is we kind of took extreme cases, right? We thought about what happens if it's covered in A, what happens if it's covered in C, what happens if the surface is bare. So instead, let's just look at the rate over the entire range. And so again, the rate was equal to some rate constant, which I'm just going to put a prime here because there's a few things in it, PA, PB. And let's go ahead and let's throw out C. We're going to say that the concentration of C on the surface is always tiny. And let's say that I'm going to hold the pressure of B constant. And I'm going to collect rate data versus the pressure of A. So first of all, what does this do to this equation? If the pressure of B is constant, can I simplify this equation? How? If I divide through everything by K2 over PB, which is what you're saying, then yeah, you get it here, and here, and eventually you can just essentially push it into the rate constant. So now you've got more stuff in your rate constant. Not that big of a deal. This equilibrium constant has also been affected, but now you just have pressure A. So notice I'm not saying that B isn't covering the surface. It's just that if the pressure of B is constant, then the concentration of B on the surface is constant. And so what I observe looks like this and not this, because I can't see this pressure dependence. Remember that in reality, this is what you derive, but this is what you observe, right? You can only observe what you can see. And if I don't change the pressure of B, how can I see that term? Yeah?
Are we missing the K4 term?
No, I said that let's assume that C is not ever on the surface.
Are you saying that K2BB is small?
No,
So why can you, I don't understand why you can just keep it.
I did it. If I divide through, now that it's constant, I can put it inside this constant and this constant. So I'm changing the definition of these two things.
Oh, I see.
The point again is that this is all that you can observe if you do this experiment. You can't observe a pressure of B term because you're not changing the pressure of B term. So this is just a constant. Yeah.
Would the PB in the numerator be absorbed into the K?
Yeah, sorry, that should have happened as well. Again, it's constant, so k times a constant, you can't tell that it's 2 constants versus 1. And it's actually like 10 constants by now because I just keep shoving crap in there. So what does this look like then? What does the rate look like as a function of the pressure of A?
Inverse curve, approximately.
You're half right.
When PA is less than 1, it grows.
Yeah, remember, imagine that I'm looking at this over a very wide range of A. That means that at some point I have a small enough pressure of A that this term is actually small and the one term dominates. And in that regime, what am I? Linear in A. And I'm starting at 0, so I have a straight line. And then in this regime, I'm A to the negative 1. In this regime, I'm A. Somewhere in between, right, these two connect. And again, what's happening here is that as I change the pressure of A, what's happening to my surface? Yeah, so in this regime, what is my surface covered in? Nothing. I know it seems silly, but that's how I say a surface is covered in nothing. And then in this regime, now I'm covered in A. Or am I? Is that correct?
Constant value.
Right.
At the top of the line, right? Or
So, I don't know what my surface is covered in. And here I don't know what my surface is covered in. So, in both of these cases, we were assuming here that B, this is true if the coverage of B is 0, but if the coverage of B is 0.5, then what would we see instead?